A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
My Weird Prompts is a community-driven initiative exploring how AI can fuel curiosity and uncover the fascinating ways our world works. GPU compute for this podcast is generously provided by Modal. Learn more at modal.com.
Hello there, Herman and Corin. So I'd love to chat today about a question that is, I think, linguistically interesting because it kind of challenges our conception of what a language is. So yesterday I was trying to create a Hebrew episode of this podcast, My Weird Prompts. And we've been in production now for more than 1,500 episodes. And the formula is that I record a prompt, or at least our original formula. I got a bit lazy lately. I record a prompt, it gets sent into our production pipeline, and then you answer using a script generated by Gemini, and your voices are generated using Chatterbox based on a voice clone. So I actually recorded 30 seconds of me speaking like Herman and Corin, and that's how the voices came to be. And for those in the technical depth of AI, these are voice embeddings that are cached. So they're always there, which actually makes a big difference in terms of consistency, so that from that sort of fairly small amount of data, 30 seconds of data, we don't get Herman and Corin sounding very different depending on the episode. That ensures a good degree of consistency. So it works very well. And we're using Chatterbox for the actual text-to-speech part. When I was trying to get it, so I wanted to do this episode, and I got the episode translated into Hebrew. That was easy. Every time we generate an episode, the script itself is saved in a database, and so it was just basically taking one in English and using machine translation. Now, it mightn't have been 100% perfect, but for the proof of concept, it was more than good enough. So the challenge was actually doing the TTS in Hebrew, and I wasn't expecting it to be so hard. The model that we use, Chatterbox, some of these models have multilingual support, which is where I think it gets really kind of confusing, because multilingual, and you've got some omnilingual models as well in speech to text, say that you can basically speak in some language, whether we know what the language is or not, and we're going to translate it into text. And likewise for TTS, the challenge in this case was the lack of vowelization in modern Hebrew. Modern Hebrew, unlike the Hebrew written in the Bible, is not written with vowels. And I saw there's actually a model, and this would be an interesting episode in itself, for the kind of niche AI community that exists in Israel. On the one hand, Israel is a major world tech center, and of course we've got some huge AI companies here, but there's also a much smaller, more focused and dedicated group of people who make tools for vowelization restoration, because it's very important for the domestic market, and that's usually how tech goes in Israel. Very, very big, well-funded tech that gets very famous, and then a sort of more maybe scrappy open source community working on these projects domestically. So I ended up finding, I think it was Minimax on Resemble. That was the only one. It took me about 4 or 5 model tests, doing my voice samples and getting that single shot voice cloning to go for my sample to read out in the target language. Now, so that's basically the answer is we will eventually get an episode out, and it's probably going to be using that. Unfortunately, Resemble Chatterbox didn't work, but some of these text-to-speech models will function in a way that is language agnostic, and that is what I'd like to talk about in today's episode. And really, what are the limits of that? Because we have different world languages, of course, but we also have different writing systems. So if you have a text-to-speech model that is capable of, instead of working at the language level where you define the speaker is speaking English and we want to speak in English, or This is a single shot voice sample in English. We'll use it to generate text in Hebrew. And that was something I was actually looking at, because some models even said they could do that. In other words, we'll learn the phonetic patterns of the speaker, and we're going to map it onto the same prosody, the same way that they speak, the same accent in a totally different language. So I'd love to talk, Herman and Corn, about how this works in practice, both on the text-to-speech side and on the speech-to-text side. Is the future of these models going to be inherently omnilingual or alingual? And we should mention as well the case of code switching, which presents its own challenges. Code switching being when somebody living in Israel like me speaks English, but we use words in Hebrew, like I want to go to the makolet. Makolet means a small convenience store. And this is something we see in a lot of immigrant populations like Hispanics in the US. And it's not an academic query of how do these models handle these cases, because that defies the concept that the speaker is speaking one language or the speaker wants to synthesize speech in one language. They're mixing and matching different ones, and that's where the traditional paradigm of STT and TTS, whereby there's often the APIs have a language parameter required that you need to say, I want speech in English, and there isn't support for multiple types. So let's talk, Herman and Corn, about the technical details in TTS and speech to text for omnilingual, and for handling these edge cases like the case of Hebrew, where you might have a language that's provided in text, but the text alone isn't the full key to tell the model how it should be read.
I was looking at my phone this morning and realized I still have to manually toggle a little globe icon to switch keyboards when I want to type in a different language. It feels so archaic, like I am shifting gears in a manual transmission car from the 1950s. It is this weird friction point where the technology forces me to stop and declare my linguistic intent before I can actually communicate. But today's prompt from Daniel suggests that, in the world of audio, those gears are basically being ground into dust. He wants us to look at the shift from multilingual AI to what is being called omnilingual speech models. The Tower of Babel problem and artificial intelligence is collapsing right in front of us. We are moving away from these rigid, language-specific pipelines and towards something much more fluid and, frankly, much more human.
It is a massive shift, Corn. For years, we have been living with what I like to call the digital sandwich. If you look at how a voice assistant or a translation app worked even 2 years ago, it was a cascaded system. You have a speech-to-text model that is specifically tuned for English, then you pass that transcribed text to a large language model to understand the meaning or translate it, then you pass that result to a text-to-speech model to generate the audio. If you wanted to do that in Spanish or Hebrew or Japanese, you often had to swap out every single layer of that sandwich for a different language, specific version. It was inefficient, it was slow, and it lost a lot of the nuance in the handoffs between models. But what we are seeing now, especially with the release of the Omni-Voice-One architecture last month in February 2026, is the total collapse of those barriers. We are moving toward a reality where the model does not care what language you are speaking because it is operating on a universal phonetic manifold. By the way, I am Herman Poppleberry, and I have been falling down this phonetic rabbit hole for about 72 hours straight. I have barely slept because the implications of moving from translation to transcoding are just staggering.
I could tell by the way you were muttering to yourself over breakfast. You sounded like you were trying to summon an ancient deity, but it turns out you were just practicing phonemes and trying to visualize high-dimensional vector spaces. So, Daniel was asking about how these models actually map a speaker's voice across languages. This is the core of the omnilingual promise. If I speak English with my usual slow, thoughtful, slightly sloth-like drawl, and then the AI makes me speak fluent Arabic or Mandarin, how does it keep me sounding like me? It is not just about the words, it is about the vibe, right? It is about the soul of the delivery.
The vibe is exactly what researchers call prosody. It is the rhythm, the stress, the pitch, and the intonation of your speech. In the old days, if you wanted to do cross-lingual voice cloning, the model would basically just take your timbre, which is the physical quality of your voice, the texture of it, and then paste it onto a generic robotic rhythm of the target language. It sounded like a hostage reading a script in a language they did not understand. There was no emotional alignment. But the new models, like Fish Audio's S2 Pro that came out earlier this month, use something called disentangled representations. This is a breakthrough in how we handle latent space.
Disentangled sounds like something I have to do with my charging cables every Tuesday morning. What does it actually mean when we are talking about a latent space in a neural network?
It means the model has learned to separate the vocal identity from the actual speech sounds and the emotional delivery. Think of it like a high-end mixing board in a recording studio. You have one slider for the physical shape of your throat and mouth, which is your timbre. You have another slider for the melodic contour of how you speak, which is your prosody. And then you have the actual phonetic content, the raw data of the language. Because these models are trained on hundreds of thousands of hours of audio across hundreds of languages simultaneously, they have discovered that human speech exists on a continuum. There is a universal latent space for phonetics. When you map a speaker into that space, the model can say, I know what Korn sounds like when he is being cheeky or sarcastic in English, and I can project that same emotional vector onto the phonetic structure of Japanese. It is not translating the words and then guessing the emotion. It is mapping the emotion directly onto the new language of sounds.
So it is essentially translating the intent and the personality, not just the dictionary definition. I saw that Smallest.ai just launched their Lightning V3 model today, March 27th, and they're claiming they can do this with almost zero latency. That seems like the holy grail for something like real-time translation. But I want to get into the weeds of how the model handles the weird quirks of specific languages. Daniel mentioned the Hebrew problem, which I know is something he deals with living in Jerusalem. It is a perfect example of why the old text-based systems fail.
The Hebrew problem is a fascinating technical hurdle because of how the language is written and spoken. In modern Hebrew, you generally do not write the vowels. You use a system of dots and dashes called Nicode if you are teaching children or writing poetry, but in day-to-day life, it is just consonants. For a traditional text-to-speech system, that is a nightmare. It is what we call orthographic ambiguity. If you see the letters M, L, K in Hebrew, that could be Malak, which means he reigned, or Melech, which means king. Without the vocalization, the AI has to guess. In the old cascaded systems, the AI would often just pick the most common version and hope for the best, which leads to total nonsense half the time.
That sounds like a recipe for some very confusing conversations, especially in a business or legal context. How do you teach a machine to guess correctly without just flipping a coin? How does it know if I am talking about a king or a reign?
You move away from the two-step process of turning text into phonemes and then phonemes into audio. Instead, you use a context-aware transformer. This is what Joseph Keshet and the team at the Hebrew University of Jerusalem have been pioneering. They use a language modeling approach where the model looks at a massive context window, sometimes exceeding 128,000 tokens. It looks at the entire sentence, the preceding paragraph, and the overall intent of the conversation. It is not guessing the vowels, it is hallucinating the correct speech units based on semantic probability. It is effectively acting like a native speaker who does not need to see the vowels because the meaning of the sentence makes the pronunciation obvious. The model understands the world well enough to know that in a sentence about a palace, the word is probably king and not reigned. This is a huge shift from phonetic lookup tables to deep semantic understanding.
It is like when I see a typo in a text from you, and I just automatically read it correctly because I know you are probably complaining about a white paper you just read. My brain fills in the gaps based on my history with you. The AI is finally getting that kind of contextual intuition. But what happens when we start mixing languages? Daniel asked about code switching. I do this all the time where I will use a tech term in English in the middle of a sentence, or if I were living abroad, I might mix the local slang with my native tongue. Most AI models I have used in the past just give up the moment I switch. They either stop transcribing or they try to force the foreign word into an English phonetic box, which sounds hilarious but is totally useless.
That is because those older models were built on a cascaded pipeline that required a specific language tag in the API call. You had to tell the system, I am speaking English now. If you suddenly dropped a Spanish phrase, the English model would try to find the closest English sounds to those Spanish words. It is like trying to play a Blu-ray disc in a record player. but the new frontier is language identification-free decoding. Models like Meta's Seamless M4T and the new DeepGram Nova 3 use an embedding space called SONAR. That stands for Sentence Level Modality and Language Agnostic Representations.
Sonar. I like it. Very nautical. Does it actually work like a ping, or is that just a clever acronym?
In a way, it does. It creates a single vector space for over 200 languages. Instead of having separate rooms for English and Spanish and French, it is one giant hall where every concept lives. When a speaker code switches, the model does not have to reinitialize or swap its brain. It just follows the vector as it moves through the latent space. If you are speaking Spanglish or Hinglish, the model treats the transition as a smooth curve rather than a jagged cliff. This is huge for global communication. We are seeing a 68% reduction in errors for complex notations like phone numbers or chemical formulas in the new 11v3 model that launched in February, largely because it finally understands the context of how these things are spoken across different linguistic borders. It is not just about the words, it is about the structure of the information.
It feels like we are finally moving away from the AI being a tourist with a phrasebook and toward it being a true local. But let us talk about the technical friction here. Herman, you mentioned the curse of multilinguality. That sounds like a title for a fantasy novel, but I assume it is actually a very annoying scaling problem for the people building these things.
It is the primary headache for developers right now. When you try to cram 200 languages into a single model, you often run into a performance plateau. If you make the model better at a low-resource language like Yoruba or Quechua, you sometimes see a slight dip in its performance in a high-resource language like English or Mandarin. It is a competition for the model's parameters. It is like trying to pack for a trip to both the Arctic and the Sahara in one suitcase. You end up with a lot of stuff that does not work for either destination, and the suitcase is too heavy to carry. This is why the architecture matters more than just the raw size of the model.
So is the solution just a bigger suitcase? Do we just need more parameters, or is there a smarter way to architect this so the languages don't fight each other for space?
The bigger suitcase approach is hitting a wall, which ties into what we talked about in the Slop Reckoning episode regarding model efficiency. The industry is moving toward mixture of experts or open-weight architectures like Mistral's Voxtral TTS. Voxtral is only a 3 billion parameter model, but it is designed to be highly efficient at the edge. Instead of one giant brain trying to remember everything at once, you have specialized subnetworks that activate depending on the phonetic input. This allows for local fine-tuning. If you are a developer in Israel and you want a model that is exceptionally good at the specific way people in Tel Aviv mix Hebrew and English, you can fine-tune those specific layers without breaking the model's ability to speak French or Portuguese. It is about modularity within the latent space.
That makes a lot of sense. It is like having a general education, but then specializing in a specific dialect or industry jargon. I am curious about the implications for the user experience. Right now, if I want to use a voice assistant, I usually have to go into the settings and pick a language. That feels so old-fashioned, like picking a long-distance carrier in the 90s. If I have a guest over who speaks a different language, my smart home should just understand them without me having to play IT support, right?
That is the goal of truly language-agnostic inference. We are moving away from APIs that require a language code parameter. In the near future, the language code will be a legacy artifact, like the floppy disk icon for saving a file. The model will just listen. It will detect the language, the dialect, the accent, and the emotional intent all at once. This is what makes the February 26 release of Omni-Voice-One so important. They showed a 15% lower latency in code switching scenarios because the model does not spend any compute cycles trying to identify the language first. It just processes the audio tokens directly. It is a unified stream of intent.
It is wild to think about. If the model can speak any language in my voice, what does that do to the concept of native fluency? If I can hop on a call with someone in Tokyo and speak fluent Japanese that sounds like me, with my cadence and my personality, am I still me? Or am I a high-fidelity deepfake of myself? It feels like we are decoupling identity from linguistic ability.
It is a philosophical shift as much as a technical one. We have always associated our voice with our identity and our language with our culture. When you decouple those, you create a world where your vocal fingerprint is portable across the entire human experience. From a pro-innovation perspective, this is a massive win. It allows American companies and technologies to integrate seamlessly into every market on Earth without the friction of language barriers. It is a form of soft power that we have never seen before. Imagine a small business owner in Ohio being able to provide customer support in 20 languages, sounding like themselves with no delay.
I can see the conservative argument there too. It is about preserving the individual's identity while removing the barriers to trade and communication. It is not about creating a global monoculture where everyone sounds the same. It is about giving everyone the tools to speak to each other while remaining themselves. If I can speak to a business partner in Jerusalem in their native tongue, but they still hear my specific voice, that builds more trust than a generic robotic translator. It maintains the human connection while removing the technical obstacle.
And it is not just about business. Think about the accessibility angle. For someone with a speech impediment or someone who has lost their voice to a condition like ALS, these omnilingual models can reconstruct their speech from old recordings and then allow them to communicate in any language. The resolution of orthographic ambiguity in languages like Hebrew also means that we can digitize and vocalize ancient text or modern literature that was previously hard for machines to parse. We are essentially giving the AI a pair of glasses that lets it see the vowels that aren't there, opening up entire libraries of human thought to the world of audio.
I am still stuck on the idea of the model hallucinating vowels. It sounds like something that could go wrong in a very funny or very dangerous way. If the model misinterprets the context, does it just start inventing a new dialect? Does it get confident in its wrongness?
It can happen. That is why the context window is so important. If you only look at 3 words, you might get it wrong. But if you look at the last 5 minutes of the conversation, the probability of error drops significantly. This is why we see companies like 11 Labs, which is now valued at $11 billion, investing so heavily in their version 3. They are not just making the voice sound better, they are making the brain behind the voice smarter. They are reducing errors in things like phone numbers and technical jargon, because those are the areas where the AI used to trip up. They are moving from simple pattern matching to actual reasoning about the sounds.
It is amazing how much of this comes back to just having a better understanding of human intent. It is not just about the sounds, it is about what we are trying to achieve with those sounds. So, if I am a developer listening to this, and I am building the next big audio app, what should I be doing right now to prepare for this omnilingual future? Because it sounds like the ground is shifting under our feet.
The first thing is to stop hard-coding language parameters into your infrastructure. If your database or your API calls are strictly partitioned by language code, you are building a legacy system that will be obsolete by next year. You need to start thinking about audio as a unified stream of intent. You should be evaluating models based on their code-switching benchmarks, not just their monolingual accuracy. A model that gets 99% on an English test but fails the moment someone says a word in French is going to be useless in a globalized market. You also need to look at end-to-end multimodal models rather than cascaded ones. The latency savings alone are worth the switch.
That is a great point. The world is getting messier, not cleaner. People are moving, cultures are blending, and our tech needs to reflect that. We should also mention the infrastructure side. Processing these massive end-to-end audio models takes a lot of horsepower. You can't just run these on a standard web server.
It really does. You cannot run these high-fidelity, low-latency models on a toaster. This is where the shift to serverless GPU platforms becomes critical. You need to be able to burst your compute to handle the inference for these complex latent space mappings. It is one thing to transcribe text. It is another thing entirely to perform zero-shot cross-lingual voice cloning in real time. You need access to H100s or the newer B200 chips to make this feel instantaneous for the user.
Which is a perfect time to mention Modal. They provide the GPU credits that power this show and make it possible for us to explore these deep technical topics. If you are a developer working on these kinds of omnilingual models, you really should check them out. They make it incredibly easy to deploy and scale these kinds of workloads without having to manage the underlying metal yourself. You can focus on the phonetic manifolds while they handle the orchestration.
They really do simplify the stack. And speaking of the stack, we should also give a shout out to our producer, Hilbert Flumingtop, for keeping the gears turning behind the scenes. He is the one who has to deal with the actual audio files and the bit rates while we sit here and talk about latent spaces and semantic probability.
Poor Hilbert. He's living in the 1950s while we are living in 2026. But seriously, this shift toward omnilingualism feels like one of those things that people will look back on as a turning point in human history. The end of the language barrier in software interfaces is going to change how we build everything from operating systems to toys. It is the final piece of the puzzle for a truly global internet.
It is the final frontier of the user interface. We went from command lines to graphical interfaces to touch, and now we are finally getting to natural, fluid, borderless speech. It is about making the technology invisible. When you don't have to think about what language you are speaking or what button to press to switch keyboards, the technology has finally succeeded in becoming a natural extension of yourself. We are moving from translation, which is a bridge between 2 points, to transcoding, which is a universal understanding.
I like that. Invisible technology. It is the only kind of technology I actually want to use. Although I wouldn't mind a robot that could translate my sloth noises into something more productive. Maybe that is the next prompt for Daniel.
I think we are still a few years away from a universal sloth translator, Corn. But for humans, the gap is closing fast. If you found this interesting, you should definitely check out some of our other episodes. We did a deep dive into the shift from traditional speech recognition to end-to-end models in episode 992, which gives a lot of the foundational context for what we talked about today regarding the digital sandwich.
And if you're worried about how much compute all of this takes, or why we are moving toward these smaller, more efficient models like Voxtral, episode 1558 on the slop reckoning covers why smaller AI models are starting to win the race. It is not always about having the biggest model, it is about having the smartest one for the specific job of phonetic mapping.
Or, as I should say, that is a very important point that aligns with the current research. We are seeing a move towards specialized efficiency within the omnilingual framework. The models are getting better at knowing what they don't need to process.
Look at you, catching yourself before you used a banned word. I am proud of you, Herman. You are learning to navigate the latent space of this podcast perfectly.
I am a work in progress, just like the models. Every conversation is a fine-tuning session.
Aren't we all? Well, I think we've covered a lot of ground today, from the phonetic manifolds of fish audio to the vowel hallucinating transformers of Hebrew University. The future of speech is looking incredibly loud and incredibly clear. It is a world where your voice is your own, no matter what language you are speaking.
It is a brave new world of audio, and I am just happy I don't have to learn 200 languages to be a part of it. I can just stay in my nerd cave and let the AI handle the conjugation.
You can barely handle 2 languages, Herman. Let's be honest, your English is already 50% technical jargon. Anyway, if you're enjoying the show, we'd love it if you could leave us a review on your podcast app. It really does help other people find us and join the conversation about these weird prompts.
Or you can find us at mywordprompts.com. We have the full archive there, plus RSS feeds and all the other ways you can subscribe. We might even have a transcript there that has been perfectly vocalized by an omnilingual model.
This has been My Weird Prompts. Thanks for listening, and thanks to Daniel for the prompt that sent Herman into a 3-day research spiral. We'll see you next time.
See you then.
Lost Dust. Goodbye.
Goodbye.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My Weird Prompts, that's the flows from sloth.